Hello and good morning. This is Craig Kozminski again with your pre-lab video for experiment number 2, time and velocity measurements for inclines and falling objects. It was a real pleasure getting to know our students last week, and we're really looking forward to this week's experiment as well. Before you proceed in watching this video, my encouragement to you is to have completely read through the entirety of the experiment. This includes the pre-lab information, the theoretical information on parts A and B, as well as the procedures. Take a special note of the lab report questions that you'll be responsible for answering for each part of the experiment. Here you'll see you have a problem worksheet. We'll talk a little bit more about this. And then also the data sheets. The data sheets is where we will be recording our experimental values that we are collecting in this week's experiment. So to begin, this week's lab consists of two parts. Part A is motion on an incline. And in part A, as you can see from the diagram here, we are going to begin with an initially motionless vehicle at the top of a ramp. And this vehicle has a flag, and the flag has a recorded width identified here as L. We're going to be recording two velocities as this car moves from the top of the ramp to the bottom of the ramp. The first velocity that we are going to be recording is the average velocity. That is the velocity of the vehicle from its beginning of travel to the end. And to determine the velocity, the average velocity, we are going to take the distance that the car travels between our two photo gates. These are the devices that we will use to time the car. And so the distance between them is d, and the total time that it takes for the car to move from photo gate 1 to photo gate 2 is our t sub s. Again, this is going to give us our average velocity. We're then going to compare this with our final velocity, and our final velocity is going to be equal to the length of the flag, that is the distance of the flag, divided by the time it takes for the flag to pass exclusively through this second photo gate. And so our average velocity is the overall time it takes, the overall distance divided by the overall time. Our final velocity is going to be equal to the width of the flag divided by the amount of time it takes for the flag to pass through the bottom photo gate. I would encourage you to, as I have done, read through the procedure, highlight or underline key pieces of information from the procedure that you think will be helpful to call attention to while you're conducting this procedure. In part B, we're going to look at the acceleration of falling objects and human response time. In part 1 of part B, as you can see here in my rough sketch, we have a meter stick. And what is going to happen is that you're going to start with your hand open at 0, and your partner is going to drop the meter stick. And what you are going to do is you're going to pinch the meter stick in between your fingers, and you're going to record the distance that the meter stick travels from 0 until you pinch it. So in this instance, I'm assuming that you've pinched the meter stick here at 10 centimeters. So your first recorded distance would be 10 cm. And you're going to do this a few times, and assuming that the object is falling with a constant acceleration due to gravity of 9.8 meters per second squared, you're going to then calculate your response time using some equations that we will call to mind here, highlighted in yellow. In part 2 of part B, what you're going to do is you're actually going to record the amount of time it takes for a tennis ball to fall a known distance of 2 meters. And so we will start the time when the object is dropped, and then when the object reaches the bottom, we will stop the timer, and that will be your t sub 1. And you're going to do this, I believe, 5 times as well. And using these times, you're going to attempt to calculate the acceleration due to gravity and compare this to the known acceleration due to gravity. So that's what's happening in part A and part B of this week's experiment. Again, make sure you read your lab report questions. This is helpful for priming your brain as to what you should be thinking about as you're doing this experiment. And so, for example, if we just read the first question, it says, discuss the average velocity as the distance as the distance the car travels increases. And then it says describe using words such as constant, increasing, or decreasing, and explain by including your data as part of your answer. And so, for example, you might say, as the distance that the car travels increases, the average velocity either remains constant, increases, or decreases. This is shown, and then this is the part where you would include your data. At a distance of 0.5 meters, we observed the velocity was this. At a distance of 1.5 meters, we observed that the velocity was this. In order to receive full credit on your lab report questions, you have to include data that is the evidence that will support your claim in the answer. So if you just say the average velocity as the car travels increases, decreases, and that's all you say, that would earn you about half credit. In order to earn full credit, you must include data in your response. Finally, on the problem worksheet, what I would encourage you to do is to look at these 4 questions. It's really 2 questions, but question 1 has 3 parts. And I would encourage you to go through and try to determine what equation you should use to answer these questions. And so to begin, in question 1, it says an initially motionless car, this means that V naught equals 0 meters per second, begins to move with a constant acceleration of 4.0 meters per second squared. And in part A, it says, show your calculations to find the velocity at times of 0, 1, 2, 3, 4, and 5 seconds. Plot the velocity on the vertical axis, so here's our velocity, versus time on the horizontal. And velocity has units of meters per second. And so what I would encourage you to do is to refer to page 38 in your lecture manual and to try to determine what form of the equation you're going to use to actually calculate the velocity given the following information. The car is initially motionless, and you have a constant acceleration. In part B, you're asked to determine the displacement using the same conditions for part A. So again, you may assume that the initial motion of the car is 0 and a constant acceleration of 4.0 meters per second squared. In part C, you're asked to use the information again from question 1 and to plot the acceleration on the vertical axis versus time on the horizontal. Finally, in question 2, it says how much time will be required to move 160,000 meters while traveling at a constant velocity of meters per second. Again, you can use some of the equations that you've learned in lecture or equations from page 38 to try to determine the correct answer before lab. Now, finally, here on our data sheet, I want to call to mind some things that might be helpful for you to look at before coming to lab. So, for example, in table part A1, you'll see that we are recording 2 times for each trial. So I'll have trial 1 and trial 2, 1 time for each trial, excuse me. And then you're going to average these together to figure out your T sub S. Then the average velocity for the run is equal to the distance that the car travels divided by the average time. And so it might be helpful for you to come in before lab having written down these equations. V av is equal to the distance divided by T sub S. Also, for the predicted final velocity, V sub f comma p, from previously or from up above in the procedure, we will see that this is going to be equal to 2 times the calculated value for this column. And so one of the things that you want to do before you come to lab is have some sort of idea which equations are going to be used in each part of the data table. In table part A2, I've given you the necessary conversion factor for converting the length of the flag in units of millimeters to units of meters, because in order to calculate the actual final velocity, we'll be using units of meters. For table part B1, you'll see that I've given you the page number in your lecture manual where you will find the acceleration due to gravity. I've already said it previously in this video, but if you don't want to go back earlier in the video, you can refer to page 40. I've also given you the conversion factor here to convert the distance that you measure as your response distance from centimeters to meters. You'll be needing that unit in meters to calculate the average response time. Finally, in part B2, to determine the acceleration of a falling object, again, You're recording time, and you'll be using that time to calculate acceleration. This is a good opportunity for you to practice determining what equation is going to be used to calculate this final column. Now, to end our video, I just want to encourage you by saying that I was very pleased with your efforts last week. Before coming to lab this week, please be certain to complete the online quiz, and I hope you have a great rest of your day. Thank you.